You're not going to want to miss this episode of the AI Show where Dmytro, a core contributor to PyTorch, walks us through how it actually works, hands-on. You're not going to want to miss it. Make sure you tune in. Hello and welcome to this special episode of the AI Show where we've invited Dmytro back because I'm a huge fan of PyTorch. Dmytro, why don't you introduce yourself, tell us who you are and what you do.
Hi, Ted. Thanks again for inviting me back. It's been a lot of fun. So today I basically wanted to talk about hands-on experience and show you some code with PyTorch and a little bit about myself. I'm one of the core developers of PyTorch deep learning framework, pretty much working on a lot of abstractions and bits and pieces and trying to make all this awesome functionality fit together and make it easy to use.
Yeah, and so last time we had a really good discussion. I loved it, but I thought this time, as you mentioned, maybe we can actually dive into some of what it looks like in code. Can we do that?
Yeah, of course.
All right, let's do it.
I have actually IPython notebook for you. So I was thinking we can just basically go through this and I can try to comment on some of the details. Again, disclaimer, this is more like very intro level part of PyTorch, just to showcasing core functionality. So kind of showing the overall libraries and flow and how you might train your actual model. The model we're going to take is pretty basic, which is basically a MNIST, but with fashion instead of digits, just so I can train it in my browser and do it pretty quickly. But of course, I mean, the same abstractions translate to much more interesting cutting-edge research. So let's get started. I mean, I'll start with just importing some PyTorch libraries. And as we talked last time, basically, PyTorch at its core is just a tensor library. You can think of it as kind of NumPy kind of equivalent. So we might just do random operations. For example, create a random matrix of numbers with different data types. Just how you would do in NumPy. You can add tensors together. You can do all the kind of fun operations in them. Similarly to NumPy, we even support kind of fancy Python-style indexing, so you can kind of slice and dice and do views and do mutable stuff like that. And the best part is that this tensor library is interoperable with NumPy. So, for example, if I create PyTorch tensor, I can call .numpy on it and get back basically the ND array from NumPy. It's a zero-copy view, so it will not actually go and copy the memory. Which comes very handy if you have like some third-party library, or if you want to call some library from NumPy ecosystem like scikit-learn in the middle of your model. You can actually do that without paying any performance penalty.
So, question here: these aren't actually NumPy tensors. There's like a full tensor library that interoperates with NumPy. I think that's an important distinction. Is that the case?
Yeah, that's correct. For example, if I do type A and type B, that one of them would be class torch tensor, another one will be NumPy ND array. But they would actually share the same memory in this case because it's a CPU tensor.
Got it.
NumPy, of course, runs just on CPU. The fun part about PyTorch, it can run on CUDA as well. So I can basically specify device equals CUDA, or just as a string. In this case, let's say we have only one GPU, and boom, I could basically create exactly the same tensor. Now it though lives on GPU, so this operation actually runs on GPU. And of course, in order to print results, I can copy it back to CPU and visualize. So that's pretty much the core of PyTorch library. Again, if you want to use just the tensor library itself and do kind of accelerated operations on CPUs, GPUs, or other devices, you pretty much can use it more or less as a drop-in replacement for NumPy. And we have pretty high compatibility in terms of APIs, and actually there's effort to kind of close that and have like complete compatibility in terms of API with NumPy. But we actually came here to do some deep learning. And again,
before we get there, can I ask a question? So in theory, you could use PyTorch tensors to do any kind of numerical computation, but then just move it to the GPU. Is that right?
Yeah. So I mean, basically, linear algebra operations work usually very fast on GPUs because of its highly parallel power. So yeah, you can think of it as pretty much a drop-in replacement for the tensor library for GPUs. Or I mean, for other devices, there are some third-party projects which kind of integrating similarly to GPU, like other devices like accelerators into PyTorch APIs.
Got it.
And so for this demo, let's grab kind of a classic example for neural network recognition, which is a MNIST data set. However, instead of digits, we'll get the more fun version of it, which is fashion MNIST. So similar to original MNIST for like handwriting digits recognition, it's basically a set of like 28 by 28 grayscale images, but instead of 10 digits, they have like 10 different types of clauses. So it's more fun to look at compared with that. So as we talked last time, PyTorch also comes with kind of set of libraries which help you to kind of get started with data reading and kind of like preparing your data, or even have like bindings to common data sets. So for something like MNIST or fashion MNIST or ImageNet or other most popular public data sets, pretty much have like one line APIs in part of PyTorch called Torch Vision. So by running this, we can basically initialize data set. Like if it's not already downloaded my machine, it's gonna go and fetch it from the internet. We can specify which transformations we want to do on images to prepare them and kind of convert them to tensors. In this case, we just do something very simple. Just take the original pixel values, kind of like normalize them so they become kind of in the range from 0 to 1, and convert them directly to tensor. Like for fancier deep learning needs, you can imagine something like some data augmentation techniques like random cropping or rotations, etc., kind of happening here. And of course, you can like write your own transform as a simple Python class as well. So by having this data set, and as you mentioned last time, like data set is pretty much just an abstraction for, hey, how many elements are there, and how do I get kind of a data element from it. This is a wrapper which knows how to index MNIST files somewhere on my machine. I'm just going to create data loader, which is, again, simple wrapper which takes a data set, takes some batch size, and spun up like a set of parallel workers, which are going to preprocess, read this data, convert it to tensors, and give me basically back an iterator so I can go through the data. And let's define some like visualization utils, which will come handy later. So in terms of dataset loader, this is basically just a Python class which I can iterate over. So I can create iterator over it, and let's try to get one sample data point from it. Let's say some images, and I asked for a batch of like 64, so it's going to be 64 images, and visualize them with regular matplotlib. Looks like some fun pieces of clauses over here, and labels would be our like kind of correct classes for each of those.
Can we scroll up for a second? I wanted to see if I understood this correctly. So basically, in the next two statements, you're basically loading a training set and a test set from an inbuilt set of data that's already available as data sets. And I'm sure there's a bunch of other data sets as well. Is that right?
Yeah. So I mean, I don't know whether like autocomplete will work here, but yeah, there is like, I mean, this is a number of image data sets which are already bound in Torch Vision. And again, like if you have your own data sets, you pretty much need to implement a simple Python class with these two methods, like give me the lens and give me the item, or kind of another variant of it, we just even support streaming, just like implement any iterator, and it will basically work with data loader, or you can use your own data loading libraries if you want as well. And you can find libraries for reading from anything from like databases to buckets in like storage buckets in public clouds and stuff like that.
Got it. And it's cool that when you're loading them, you can actually transform the data as it's loading, because the transformers go directly into the data set. So what's the difference between what's the job of a data loader versus a data set versus a transformer in like a sentence?
So data set is more like you can think of it like a dictionary semantics, right? Like which data there is. So data loader is more of a multi-threaded worker, or multi-process worker, which would take a data set and like try to sample some items from it. In this case, with some shuffling, group them into batches of a given size, and apply transforms which were specified on the data set, kind of as a part of those separate multi-processing workers. So from your actual Python training script perspective, you already get like prepared tensors, and you don't have to wait in your main process for pre-processing to take place. So this is kind of like a simple setup, which works quite well for a lot of for kind of like getting started, and probably for like small to mid-scale data sets. I mean, for like the most like highly scalable use cases. I mean, if you're probably reading some like proprietary data in a huge scale from your own storage, I mean, you might as well just implement your own like library for data reading. We do whatever you want, but kind of data loader and data sets usually work quite well for kind of like reasonably big use cases and kind of give you default performance pretty nicely. So let's move on to actually network architecture. As I described last time, PyTorch comes with basically library of standard neural network layers, and in this case, I'll define like very simple network. So I inherit my class, which represents my my network from an end module, and in this case, it will be just for layers, like multi-layer perceptron. So I'll just use fully connected linear layers. So I'm going to create them with respective sizes, and I'm going to tell how like my network is going to be applied to an input tensor. So my input is going to be an image, right? So it's going to be like some dimensions, channel dimension, and first dimension being the batch size. So I can apply my network to multiple images. So what I'm saying here is let's take and reshape kind of view this input tensor as a just every pixel having its own value, because we're going to feed it into fully connected layer. So I'm just saying that, hey, I want to keep the batch dimension, and all the other dimensions I want to collapse into one. So now the x is going to be there. Like after this x is going to be just two-dimensional tensor with batch dimension and kind of all the pixels in one row. Right. And I'm just going to apply my fully connected MLP. That's it. And those like softmax in the final layer to kind of do classification, so I can feed it into classification loss.
So here's a question, and I'm glad you're here so I can ask you this. So basically, do you store in the init function? You're basically storing the things that store the model parameters, and in the forward, you actually run the functional stuff, because I see that the activation functions are in there as well as the final activation function is in there as well. So basically, you store the things that store model parameters in the init, and in the forward, you run the functions. Is that accurate?
Because I mean, Relu in this case, for example, doesn't actually have parameters, so we can just use the functional version. However, for like something like linear layer, there is actually like state associated. There are weights, so that's why it makes sense to kind of like store it explicitly in the state, and also allows you, like, I mean, if you were to do something like parameter sharing, for example, so for whatever reason I want to use, let's say, the same parameters in the first layer and the third layer of neural network, I can basically just change it something like this and call the same layer multiple times. So in this case, first and third layer will actually share the same parameters, but they will be applied multiple times in the network. I mean, cool. It's not really useful in this particular case, but might be useful in other cases. So this is just a Python object, right? So we can effectively just create our model. We can move our model to GPU, and it will actually go and like move every parameter of the model to GPU. So the class basically ends up being just a Python class. But if I'm going to look at model.fc1.weight, it will be like a tensor living on GPU. And similarly, I can like define my my loss and my optimizer. In this case, I'm just taking like simple log loss for classification, and I'm also taking like the simplest possible optimizer, just vanilla SGD. I mean, again, you have like all the other kinds, from like Adam to Adagrad to all the fancier options. And to your question about kind of visualizing parameters, right? We can do something like model fc1.weight, right? And it will be just a tensor. I mean, because we just created our model, it's going to be randomly initialized, leaving somewhere on GPU. So you can see that it lives on like GPU 0, and also because it's by default it has like requires grad equals true, which means that if I'm going to do some operations with this parameter, actually AutoGrad is going to remember those operations, so I can do backwards later on. So actually, let's try that. So as before, we're going to fetch one batch of images and one batch of labels. We're going to move our images to GPU because our model is there. You're going to basically apply the model to the inputs. So it's called model.forward. Compute our like predicted predict like softmax outputs and feed them into our log loss criteria, which we defined. And then we're going to say loss.backward. So effectively doing like false operations which happened inside the model. Autograd was remembering which operations were there, like which matrix multiplication, so like real application, etc. And loss.backward is going to walk backward this kind of tape, this graph of operations that happened, and assign like compute the gradient values and assign for every parameter dot grad the actual tensor of what should be the gradients for this input starting from this loss. So for example, if I run it, I can see that like now my like fully connected layer weight parameter has dot grad attribute, which is tensor by itself of the same size, which are like some gradients of this tensor for this inputs. And every time as I'm going to run it on different inputs, of course, gradients will change and parameters will change because I will be calling like actual optimizer later. But I'm just showing that like it's pretty kind of componentized, and you can use individual pieces independently if you wanted to.
That's cool.
So to make our training loop a little bit more fun, let's start with some visualization. So PyTorch actually has built-in integration with TensorBoard, which is like this great project built by Google, which is actually independent from TensorFlow. So you can use it for kind of visualizing graphs, visualizing kind of learning process, or like some fancier like embeddings visualizations or images and stuff like that. So let's set up some TensorBoard. Let's also actually look at how those images which we feed in our training look like. I mean, pretty much. Pretty nicely, especially after normalization. You can see that like background became white and it's just single scale image now. So here comes the interesting part, which is actually our training loop. And PyTorch Core library itself basically just gives you bits and pieces, so you can build your own training loop with whatever flexibility you want. And that's what we're going to show here. Of course, if you're like building your actual application, or like if you're using some higher level framework, usually you would be using some of the kind of libraries on top. For example, PyTorch Lightning or PyTorch Ignite are kind of two popular choices for abstracting out a lot of boilerplate from the training loop. So they kind of like the logic which we spell out here kind of behind the scenes, and provide a lot of kind of tweaks and configurations for the common situations. But in this for this demonstration, let's actually build our own. So what we're going to do, we're going to take several epochs, right? So we're going to go through our training data multiple times. And every time I'm going to just take my input loader, which is going to be shuffled every time, take some images and labels, just as we did before, run my model, calculate loss, prepare optimizer, call loss.backwards, and do optimizer.step, which is going to do an SGG step. And let's do like some of our kind of manual metrics computation, which is just like a running loss as we run it. So if I run the cell, you can see that it's running. I'm also, after every epoch, I just spelled out it explicitly. I'm gonna take my test set, and I'm gonna run my model on it and compute kind of like maximum class, which is what actually our model predicts for every image, and just spelling out it manually in Python, compute like whether the model got it right or not, and compute the accuracy, which is basically just like the ratio of images which our model classifies correctly. And as you can see here, I mean, our model trains, right? So training loss goes down, our test accuracy goes up. I mean, if I keep it training, it will probably reach, for the simple model, maybe like around 90% accuracy or something like this. I mean, again, it's a very simple data set, so even a very simple multi-layer perceptron trains pretty well. Yeah.
Let's go up there, because I want to make sure I can see what's going on. So basically, it's literally just the training loop. And the 5 important things in the training is, obviously, you need to call the model, you need to calculate the loss. And then this is an interesting thing. Why do we have to do 0 grad on the optimizer? Because the optimizer, my sense is that the optimizer has all of the model parameters sort of built in.
Yes. Yeah. So I mean, this is more like an explicit convention. If you use this kind of backwards API, it actually, in some cases, you might want to call .backwards multiple times, because you might have like multitask learning and you might have multiple losses. So you want to actually add gradients for those together. So that's why kind of in canonical PyTorch, you need to call zero grad explicitly to say like, hey, I want to actually like discard my previous gradients and compute the new ones. If I didn't have this, then gradients from every dot backward call would be like kind of accumulated together, just like added together, which is useful in some cases, but for like canonical for the canonical neural network training, you just want to clear them up every time.
So where, because if we're looking at, like, for example, I think you were using stochastic gradient descent, where is the subtraction of the gradients of the model parameters happening on the model parameter? You know what I'm talking about? Because you got to subtract a scaled times the learning rate and the
so that's basically what optimizer.step does, because we created in this example we created optimizer.sgd, right? So that's what it does in implementation. I mean, if we wanted to do this example even more kind of low level, we could have written here something like iterate over every model parameter and basically do something like for param in model parameters, do something like param minus equals, param.grad something, right? Like times like learning rate or whatever. So that would work. Something like that would work too. But in this case, I'm just calling the higher level API, which kind of abstracts it out.
Awesome. And so that's why, for example, when you're doing the test part, you say no gradient, because you just don't want those. You don't want those calculations to even be done, because it doesn't matter.
Yeah. So actually, I don't have to call no gradient per se. Because if I don't call backwards, it would actually will not call backwards pass of the model. It still help. It's still helpful to do this because like it disables tracking of autograd. So maybe it has like small performance benefit, because PyTorch doesn't need to remember like which operations kind of happened in forward, because it knows that like backward will not be called. However, even without it, it would work just fine, because as you can see, we just don't call dot backward for our loss. We don't even compute loss for the test set evaluation. We just,
and then the last question sorry about that. And then the last question, you explicitly set the model to eval versus train. What does that do?
Yeah, so this is more like switches a setting, kind of like global setting on the model. So there's like parameter called like model.training. On every module there is like a field like this. So it's basically the same as like saying something like this: model training equals true. Actually, for this model we don't have to do it. There are some modules which do differ between evaluation mode and training mode. Most obvious example is dropout or like batch norm, right? Where like, for example, for dropout and training, you would want to generate like random mask and apply it to the model. And during evaluation, you actually just correct for that by multiplying by some global rate, because you don't want to randomly disable some of the neurons. But in our case, we actually don't use any of those modules in our model. So technically, you don't have to do that, but I'm just showing it for general completeness.
Love it. All right, let's keep going, my friend.
Yeah. So we, as you might have noticed, we were using this like TensorBoard writer along the way to add our training statistic here. So let's actually try to launch TensorBoard, and it can be launched as like a separate web page, but also it has pretty cool integration inside IPython notebook. So I can see some of the like our training graph, which is not very interesting, but it goes down, which is good, which we logged over there. We also logged about some of the sample images, so there's visualization for that. Also, somewhere above we logged their graph of our module. So basically, which operations like PyTorch implemented kind of were called inside our module CNN module, kind of can be seen in the graph form. It's not very interesting for our model, but it's probably more interesting if there are like more complicated structures and you want to see kind of graph representation instead of the code. Again, TensorBoard is awesome. It's a great project, and there are like much more visualization integrations there. So if you have like embeddings visualizations 3D or something like this, that might be a good tool. So apart from TensorBoard, we can also just use any part of a regular Python scientific ecosystem. So in this case, like let's try to do our own visualization. This is just some matplotlib code which visualizes predicted classes with a cute graph. So if I want to explore how my model works, for example, I can take test dataset, run my model just like how we did it before, and for example, paint like predicted class for every image. So our model actually learned some stuff. So it has
about almost 90% accuracy, right? So you can say that for something pretty obvious like pants, it does recognize this as trousers. This is hard to say even for me what type of clothes it is, but for something like dress or pullover, it's pretty well classification and predictions. And as you mentioned before, basically our model, all learning is kind of captured in our model's parameters. So there is this helpful method state, which is basically just returns you a dictionary of the parameters inside the model. So all that our model learned is basically in those few tensors, which means that if I, for example, want to save the state of my model so I can later deploy it somewhere, or just want to kind of save a good model which I obtained, I can take this dictionary and basically do torch.save on it, which you can think of as like kind of more optimized pickle implementation, which can understand PyTorch tensors, save it into a file, and later on basically like load from stadic as well by taking like model and doing load from stadic later on. So this way of saving PyTorch models basically just saves the parameters. So if you do that and you kind of want to later run your model, you still need to have the source code of your model, basically that kind of class definition which we have had above, which works in majority of cases. But for cases when you actually want to package together both model and the source code, and for example, deploy it for some embedded inference or deploy in some environment which might not even have like Python, there is this whole part of PyTorch called Torch script, so or called JIT also. So you can basically do torch.jit.script on a model. So what it's gonna do is gonna like go find all the source code bits which are needed in order to run your model, not actually initialize it, but just run. So it's the forward parts. Take all the state of the model, so basically all the kind of classes and then module classes which your model consists of, and basically save them in our own like self-contained package. So that that package is basically doesn't depend on Python at all. So you can even use C++ API to deploy it. So if you later on want to run it on your mobile phone, or you want to run it on your embedded into some application you might have, and you don't want to kind of carry Python ecosystem with that, that's a pretty useful way for deployment.
And that's really cool, right? Because like basically in the state dictionary, you have all of the parameters and everything that it learned in there, so you can do other things with it too if you like.
Yeah, you can visualize it. You can, I mean, there are a lot of libraries for like understanding neural networks. Some of them in PyTorch ecosystem, some of them kind of on third-party. So I mean, you can basically look at that. You can kind of transfer it to a different model. And sometimes people even, if you do kind of fine tuning, or if you are doing like transfer learning, so you basically want to take some of parameters from the base model and like add a few layers and train it once more on some data set which is more specialized to your task. People do a lot of that both in the image or especially in NLP, because like fine tuning transformers is now very popular. It's very natural how to do that, because you can basically just see what the parameters of your model are. This is a Python dictionary. You can like go tweak it if you want. So that kind of fits into general point of PyTorch being like very explicit and kind of being very kind of embedded in the Python ecosystem and thus intuitive to use. Kind of as another demonstration for that, like if we go back, for example, and go back to our model definition, I mean, this model is just a Python object, right? So I can do, if I'm trying to debug something, right, I can basically go and like do a print statement here. I can, for example, print shape of my tensor over here and shape of my tensor over here, and maybe like print whatever the result was, right? So now if I run my model, and for example we run this part, you can see that whatever like print statements we put there, I just run as a part of like regular implementation. There's no magic. This is basically just a Python program, and this is really powerful because I could put like a debugger here. I could invoke PDB here. I can invoke any kind of third-party library if I wanted to, and which really makes PyTorch kind of a pluggable library with the rest of the ecosystem. And there are people kind of exploiting this functionality for pretty much connecting it to all the different domains or all the different libraries from other parts, ranging from some more like domains for deep learning to like optimizing differential equations and stuff like that in kind of more scientific compute areas.
All right, so let's go down all the way to the end just to make sure, just to wrap this up. Basically, if you want to save and load the model, you have those. You basically save the state dictionary. It does a checkpoint, and then you can load it up. Load up a saved model as well, right?
Yeah. So load from state dictionary, and that's pretty much what be it. And in this case, this is actually a bundle which I can load back, and it will be just self-contained model which I can do in separate, Python process or even C++ process without even having to have the source of the model available, because source of the model is actually packaged in the same archive. So that's pretty much wraps up our short demo. If you want to learn more, go to PyTorch.org. It has a lot of tutorials and blogs and documentation, and pretty much all the tutorials are structured as also Python notebooks, like Jupyter notebooks, so you can run them. You can run them. It's easy to kind of tweak them and get started. Also, I talked a little bit about serving, for example. That's probably for another demo, but you can go to PyTorch Serve and grab kind of model server implementation, where we can take this model and pretty much with few commands wrap it in a simple a simple server which will expose REST endpoints, so we can, for example, from our application, start sending requests and do inference on our model somewhere in application.
Well, Dmytro, this has been really awesome. I love how we went through everything step by step. Thanks so much for spending some time with us. And again, those of you that are watching, thank you so much for being with us. You've been learning all about PyTorch hands-on. Thanks again to Dmytro, and hopefully we'll see you next time. Take care, my friends.